Now let's look at an example of solving an initial value problem by using Laplace transform. So this is one that we could solve anyway. We have y double prime plus 7y prime plus 10y equals, in this case, 0. And we're told that y of 0 equals 1 and y prime of 0 equals 1. Okay, so what we do is we just take the Laplace transform of everything. So what I know then is if I take the Laplace transform of the left-hand side, I'll have the Laplace transform of y double prime plus 7 times the Laplace transform of y prime. I'm just using that linearity property, plus 10 times the Laplace transform of y, and then equals the Laplace transform of 0. Okay, but now the Laplace transform of 0 is just 0, because if we multiply 0 times anything, even though we take the integral, we just get 0. And so now we just need to use so here we use the linearity property. Now we use that derivative property. And so again, if I just say that the Laplace transform of little y is this uppercase y, then I don't want that to look like a minus sign. So then here we use our property and we say, well, that's s squared y, and then minus, and remember we laddered down, so this is s to the first, and this is y of 0 minus s to the 0 y prime of 0. And then we have plus 7. Now be careful because this is 7 times that whole thing, so I've got a parenthesis, and again we'll get s times y, so just s to the first because it's first derivative, and then minus y of 0, and plus 10 times y, and that equals 0. Now, if I collect up the y terms, which I will always be able to do, notice I have s squared y, I have a plus 7 sy, and plus 10y, like that, and that's all equal to s times y of 0, I'm just moving that over to the right-hand side, and then plus y prime of 0, and I have a plus 7y of 0. Okay, so I have all that. Now I know that the y prime of 0 and the y of 0 are both 1. And so on this side I'm going to factor out that y. I have s squared plus 7s plus 10. And on this side I have s times 1 plus 1 plus 7 times 1. And so on this side I get, what, s plus 8. So this is s plus 8. Which means then y, the Laplace transform of the original function we're looking for, is equal to s plus 8 over s squared plus 7s plus 10. Awesome. Now, here's the problem, right? I need the inverse Laplace transform of this right-hand side here. If I have that, then I can tell you exactly what little y was. So there's the rub. Okay, well, so that's going to take some work. Often it's going to take partial fractions. And so first I'm going to factor this thing. This is s plus 8 over s plus 5 times s plus 2. Okay, now I'm not going to go into the partial fractions right here. We can always do a review of that, but using partial fractions, I can rewrite this fraction as 2 over s plus 2 minus 1 over s plus 5. Okay, and you can check that real quick, right? If I get a common denominator of s plus 2 times s plus 5, I end up with the numerator of 2s plus 10 minus s minus 2, and notice that that thing is equal to s plus 8 for a numerator. So that does work, and so that's our partial fraction. Now you can actually get Sage to do partial fractions for you, so that's nice. But so that's our Laplace transform of y. And so then what we have to do is go to the table to try to figure out what the heck this is. And what we find in the table is that e to the at goes to 1 over s minus a. And so here we have y of t is equal to, well, if I look here at this first one, I've got an extra 2, so I'll have to multiply by 2 because we've just got 1 minus. And then the a is has to be, it's a minus a, so this is actually a is negative 2 in this first one. And so I get 2e to the negative 2t from that part. And then here I'll get minus, and here a in this inverse Laplace transform is negative 5, and so we'll get e to the negative 5t. Okay, and there's our solution, complete with our arbitrary constants and so forth that we had to get from the initial conditions. So looking at it real quick, back here, so we had, if we did this with our other method of the characteristic polynomial, I've got r squared plus 7r plus 10 equals 0. And so notice, that was just this polynomial right there. We just have it in s instead of r. And it factored. And so the zeros of that turned out to be minus 5 and minus 2. And so we know that, yeah, that's right. If we had solved this using the previous technique from chapter 4, we would have had a y equals some c1 e to the negative 2t plus c2 e to the negative 5t. And we would have had that y of 0 is equal to 1, and well, so that would mean c1 plus c2 is equal to 1. And notice our c1 and c2 here, we have a 2 and a negative 1. 2 plus negative 1 is 1. And then if we would have taken the derivative, right, y prime is equal to negative 2c1 e to the negative 2t plus negative 5c2 e to the negative 5t. And then running out of room here, y prime of 0 is also equal to 1. And so for that equation, we'd have ended up with minus 2c1 minus 5c2 is equal to 1. And we could have taken that equation, multiplied the top one by 2, add them together. If I do that, the c1's cancel, and I get minus 3c2 is equal to 3, because I had 2 times 1 plus 1. and so C2 is equal to -1. Huh, I've seen that somewhere before, right up there. But if C2 is equal to -1, then C1 is equal to 1 minus a -1 from that first equation, and so C1 is equal to 2. And so you see, we do get that same solution. We could have done it either way. It's interesting with this Laplace transform that it, by the nature of using y0 and y prime 0 up here, that we already take care of those constants in that process. But at any rate, that's one example of how we use Laplace transforms. That was a pretty straightforward one, about as straightforward as they get. We can look at a partial fraction, but also we can look at Sage and see how to do partial fractions with Sage. So I'll do a couple quick videos on those. So okay, there's example 1.